In question 1, we want to use the intermediate value theorem to find an interval in which this equation, e to the x minus x cubed equals 0, where this equation has a root. Here, when we're doing this, we just state any conditions important in the application of the theorem. Well, the first thing to mention is that the intermediate value theorem applies to any continuous function. So firstly, the function we are dealing with here is f of x equals e to the x minus x cubed. And this function is continuous everywhere. Right? So no matter what interval we pick, this thing's going to be continuous on that interval. Great. That condition is good. Next thing we're going to need to do is we're going to need to actually find an interval where one endpoint is above this number 0 and the other endpoint is below this number 0. Well, let's suppose we pick f of 0. F of 0 is e to the 0 minus 0 cubed, which is e minus 0, so e to the 0 is 1, which is 1 minus 0, which is 1. Okay, this one's bigger than 0. Let's say I picked f of 1. That's e to the 1 minus 1 cubed. Well, e to the 1's e minus 1's approximately 1.7. This is still above 0. However, if we pick f of 2, here we get e to the 2 minus 2 cubed. If we approximate this is about 7.39 minus 8. This actually turns out to be less than 0. So since f of 2 is less than 0, and f of 0 is bigger than 0, if we pick the interval from 0 to 2, right, there is a c in the interval from 0 to 2 such that f of c equals 0, right? That's what the intermediate value theorem says. So if we've got an interval and if one endpoint's above a number, the other endpoint's below a number, there's some point in the interval such that this equation is true. Now, what does f of c equals 0 mean? It means that e to the c minus c cubed equals 0. Basically, that we have a root to this equation. For question 2 here, we have the function f of x equals x squared plus 3x minus 1. And we want to use the limit definition of the derivative to find f prime of 1, to find the derivative at 1. Now, since we're trying to find f prime at a point, f prime at 1, we're going to use this limit definition of the derivative. F prime of a is the limit as x goes to a of f of x minus f of a over x minus a. So then a here is 1. So f prime of 1 is the limit as x goes to 1 of f of x, which is x squared plus 3x minus 1, minus f of a, which is 1 squared plus 3 times 1 minus 1, all over x minus 1. Now we're going to simplify this thing. It's still the limit as x goes to 1. The x squared plus 3x minus 1 we can't simplify yet. 1 squared plus 3 times 1 is 4. 4 minus 1 is 3. So we're going to subtract 3 from this whole thing. We divide by x minus 1. So we get the limit as x goes to 1, x squared plus 3x minus 4 over x minus 1. Now if we plug in 1 to the top and 1 to the bottom, we're going to get 0 on the top and we're going to get 0 on the bottom. If we ever have 0 over 0, one of the methods we can use to deal with this is factoring and canceling. So we're going to try to factor the top and the bottom. The top factors as x plus 4 times x minus 1. The bottom is just going to be x minus 1. The x minus 1's cancel. We have the limit as x goes to 1 of x plus 4, which gives you 1 plus 4, which is 5. So for this function, f prime of 1 is 5. For question 3a, we want to find the limit as x goes to pi over 2 of cos x minus sin x. So with any limit question, the first thing we should always try is just plugging in. So we plug in pi over 2 for x, we get cosine pi over 2 minus sine pi over 2. Cosine pi over 2 is 0, sine pi over 2 is 1. 0 minus 1 is negative 1. That's it. This limit is just negative 1. We don't have to do anything more than just plugging in pi over 2 for x. For question 3b here, we want to find the limit as x goes to 4 of squared x minus 2 over x squared minus 6x plus 8. As with any limit problem, we should always start by plugging in. We plug in 4 for x. we get square root of 4 minus 2 over 4 squared minus 6 times 4 plus 8. Square root of 4 is 2, 2 minus 2 is 0 on the top. 4 squared is 16, 6 times 4 is 24, 16 minus 24 plus 8 is 0 on the bottom as well. Since we have 0 over 0, we're going to try to find some other method to apply to this problem. We can't factor and cancel because we cannot factor the top. So what we're going to do is we're going to multiply top and bottom by the conjugate. So we're going to have the limit as x goes to 4, square root x minus 2 over x squared minus 6x plus 8. We're going to multiply top and bottom by the conjugate of the top, by square root of x plus 2. When we do that, the top will become x minus 4. The bottom, well, for the bottom, we're going to factor this guy, x squared minus 6x plus 8. When we factor that, it's going to factor as x minus 4 times x minus 2. And we're still going to be left with this square root x plus 2 here. When we do these, x minus 4's cancel, and we're going to have the limit as x goes to 4, 1 over x minus 2 times square root x plus 2. So next, I'm going to try plugging in again. I have canceled, so now I can try to plug in again. Plug in 4 for x. We have 1 over 4 minus 2 times square root 4 plus 2. 4 minus 2 is 2. Square root 4 is 2. 2 plus 2 is 4. So you have 1 over 2 times 4, which is 1 over 8. So this limit gives us 1 over 8. For 3c, I want to find the limit as x goes to 2 of x squared minus 6x minus 7 all over x squared minus 4x plus 4. The first thing I'm going to do is I'm going to plug in 2 for x. I'm going to get 2 squared minus 6 times 2 minus 7 on the top. I'm going to get 2 squared minus 4 times 2 plus 4 on the bottom. 2 squared is 4, 6 times 2 is 12, 4 minus 12 is negative 8. Negative 8 minus 7 on the top gives you negative 15. On the bottom, 2 squared is 4, 4 times 2 is 4 minus 8, which is negative 4 plus 4 gives you 0 on the bottom. Since we have a non-zero number over 0, this limit's either going to go to positive or negative infinity. But to figure out which, we have to take the limit from the left and the limit from the right. So first we're going to do the limit as x goes to 2 from the left. To do that, we're going to plug in some number which is close to 2 but not quite equal to it. Say x equals 1.9. When we do that, we're going to get 1.9 squared minus 6 times 1.9 minus 7 all over 1.9 squared minus 4 times 1.9 plus 4. When we evaluate this, this gives you negative 14.79 all over 0.01. This will give you a negative number. So therefore, the limit as x goes 2 from the left goes to negative infinity. Now I'm going to try the limit as x goes to 2 from the right. Here I'm going to plug in something a little bit bigger than 2. Say x equals 2.1. When I do that, I get 2.1 squared minus 6 times 2.1 minus 7 all over 2.1 squared minus 4 times 2.1 plus 4. When I evaluate that, on the top I'll have negative 15.19, and on the bottom I'll have 0.01 again. This also gives you a negative number, so this limit also goes to negative infinity. Since the limit from the left and the limit from the right both go to negative infinity, the whole limit, the limit as x goes to 2 of x squared minus 6x minus 7 all over x squared minus 4x plus 4, that whole limit equals negative infinity. In question 3D, we want to find the limit as x goes to infinity of negative 2x to the fourth plus x squared minus 5 over x cubed plus x minus 7. Now if I plug in infinity for x, I'm going to have negative 2 times infinity to the fourth, which is basically negative infinity. We're going to have a plus infinity, we're going to have a minus 5. On the bottom we'll have an infinity plus another infinity minus 7. So the key thing is you got infinity both on the top as well as on the bottom. If we ever have a situation with infinity both on the top of a fraction as well as on the bottom of a fraction, what we're going to do is we're going to divide the top and bottom of the fraction by the largest common power. The largest power which goes into both the biggest term on the top and the biggest term on the bottom. Biggest term on the top is x to the fourth, biggest term on the bottom is x cubed. So I'm going to divide the top and bottom by x cubed. So when I do that, I'll get the limit as x goes to infinity. When I divide negative 2x to the fourth by x cubed, I just get negative 2x. Divide x squared by x cubed, I get 1 over x. Divide 5 by x cubed, I get 5 over x cubed. At the bottom, I'll have a 1, and I'll have a 1 over x squared, and I'll have a 7 over x cubed. Now when I plug in infinity for x, that'll give you negative 2 times infinity plus 1 over infinity minus 5 over infinity cubed all over 1 plus 1 over infinity minus 7 over infinity cubed. I guess this should be infinity squared as well. This thing, this thing, this thing, and this thing all go to 0. That means what we're left with is just a negative infinity on the top. Negative 2 times infinity is negative infinity. Divided by 1. Dividing something by 1 never changes it. So our final answer for this limit is negative infinity. In question 4 here, we've got the function g of x equals x squared. And we want to use the limit definition of the derivative to find the second derivative, to find g double prime of x. So, first, before we can find the second derivative, we've got to find the first derivative. So g prime of x is going to be the limit as h goes to 0 of g of x plus h minus g of x over h. Notice I'm using this definition of the derivative rather than the limit as x goes to a1 because we're trying to find g prime of x rather than g prime of a specific number. So now I am going to plug in the formula for g of x. We'll get the limit as h goes to 0, x plus h squared minus x squared over h, which gives you the limit as h goes to 0, x squared plus 2xh plus h squared minus x squared over h. These x squareds are going to cancel, so we will get the limit as h goes to 0 of 2xh plus h squared over h. If I'm dividing this whole thing by h, I can divide each term by h. If I divide the first term by h, I get 2x. Second term by h, I just get h. So we have the limit as h goes to 0 of 2x plus h, which is just 2x, because this h is going to go to 0. So the first derivative is 2x. Now if I want to find the second derivative, I've got to apply that same definition again. The limit as h goes to 0. But here I'm going to apply it to the first derivative. I'm going to take g prime of x plus h minus g prime of x over h. So I'm going to have the limit as h goes to 0. G prime of x plus h is going to be 2 times x plus h. G prime of x is going to be 2x. Then I've got to divide by h. That gives you the limit as h goes to 0. If I expand the 2x plus h, I get 2x plus 2h. Then we subtract 2x, divide by h. The two x's will cancel. I'll be left with the limit as h goes to 0 of 2h over h, which is the limit as h goes to 0 of 2, which is just 2. This means that the second derivative of this function, g double prime of x, is 2. In question 5 here, we want to locate all points at which this piecewise function here is discontinuous. The first thing to note is it's a piecewise function, and each piece of the piecewise function is itself continuous. So we don't have to worry about any continuity problems there. The only places we might have continuity problems are at what are called the transition points, the place where it switches from one formula to another. It switches from the first formula to the second at x equals 0, and from the second to the third at x equals 1. So first we're going to check for continuity at x equals 0. So I'm going to start by taking the limit as x goes to 0 from the right of f of x. Well, if I'm approaching 0 from the right, I'm a little bit bigger than 0, which means I'm going to be using this second formula. I'm going to get the limit as x goes to 0 from the right of 1 over x. Now if I plug in 0 here, I get 1 over 0. So we have a non-zero number divided by 0, so this limit's either positive or negative infinity. Positive and negative infinity are two special ways in which this limit cannot exist, which means this limit here certainly does not exist. If this limit does not exist, the function cannot be continuous, because for it to be continuous, the limit from the right, limit from the left, and the value of the function must all exist. So because the limit as x goes to 0 from the right of f of x does not exist, f of x is discontinuous at x equals 0. Next, I've got to check x equals 1. So I'm going to do the limit as x goes to 1 from the right, the limit as x goes to 1 from the left, and f of 1. So if I'm approaching 1 from the right, I'm a little bit bigger than 1, I'm going to use that formula. The last formula, which is x squared. Plug in 1 for x, I get 1 squared, which is 1. If I do the limit as x goes to 1 from the left, I'm going to use this formula. It's going to apply when x is a little bit smaller than 1. So I'm going to have the limit as x goes to 1 from the left, 1 over x. Plug in 1, I have 1 over 1, which also gives me 1. Now if I plug in f of 1, then x is actually equal to 1. When x is equal to 1, I use this formula here. So it's going to be 1 over 1, which also gives me 1. Since these three numbers are all the same, f of x is continuous at x equals 1. So the only place it is discontinuous is at x equals 0. In question 6 here, we have the graph of a function g of x given down here. We're going to use this graph to solve a number of questions, to find a number of properties of this graph. The first one they want us to find is the limit as x goes to 2 of g of x. Well, this is a two-sided limit, so here we're approaching x equals 2 from both sides, which means we're going this direction along the graph and this direction along the graph. Either way, we approach this point, which is at y-coordinate 2, so this limit is 2. For the next one, we have the limit as x goes to negative 1 from the right of g of x. So here's negative 1. We're approaching x equals negative 1 from the right, which means we're approaching along this line. We're going to approach this point here, which is at x equals y equals negative 1. It's also at x equals negative 1, but the y coordinate is the one we put in the limit. Now here, if I ask you the limit as x goes to negative 1 as a two-sided limit, I'm saying I'm approaching negative 1 from either side. Now from the right it goes down here, but from the left it goes up off to infinity. Since the limit from the left goes off to infinity, the limit from the left does not exist, so the two-sided limit does not exist. If I want to take the limit as x goes to 0 from the left of g of x, well, I'm approaching 0 from the left, which means I'm approaching here towards this point. The y-coordinate of that point is negative 1. If I want to take the limit as x goes to 0 from the right, we approach 0 from the right. If I approach along this line, I am approaching that same y-coordinate of negative 1. Now, if I want to take the limit as x goes to infinity of g of x, that means I'm taking the limit as x goes to infinity. I'm going as far to the right as possible. If I'm going as far to the right as possible, I'm following this arrow up here. That arrow goes up, so the y-coordinate here is going to go to positive infinity. If I take the limit as x goes to negative infinity of g of x, I'm going to be following this line here that goes to the left. Notice that this line here is getting closer and closer and closer to this asymptote here. This asymptote goes through y equals 2, so this limit goes to 2. The second part of this question asks us to locate all x values at which this function is not differentiable. So there's a couple of things I'm looking for when I'm looking for it's not differentiable. First, I'm looking for places where it's not continuous. Well, it's not continuous here, because you've got a hole in the graph of the function and a point down below. So it's discontinuous at x equals 2. It's also discontinuous here, because the limit from the left and the limit from the right are different. So it's also discontinuous at x is negative 1. At either of those places, it is not differentiable because it is discontinuous. There's one more place where it's not differentiable, and that's a place where it is continuous. But here, it is not differentiable because there is a sharp corner in the graph. Anytime you have a sharp corner, it is not differentiable. So there's a sharp corner at x equals negative 3. So these three x values, x equals negative 2, negative 1, and negative 3, positive 2, negative 1, and negative 3, those are the three places where this function is not differentiable. For question 7, we're given the graph of a function f of x. We want to sketch the graph of its derivative. To do this, what we're going to do is we're going to look at a bunch of different points in the graph of this function and find the slope at each of those points. So let's first talk about the point down here where x is negative 4. If we look at the tangent line here, the slope of that tangent line is a very small positive number. It's going up but very little. So let's say the slope here is approximately 1/4, let's say. Now if we go to negative 3, if we draw a tangent line at that point, we've got a slope which is definitely steeper. That slope's getting much closer to 1. So let's say the slope is going to be 1 there. Here, at negative 1.5, we've got a horizontal tangent line, which means we have here a slope of 0. At 1, we've got a tangent line that looks approximately like this. Here this slope is approximately negative 1. Sorry, at x equals 0. At x equals 1.5 here, we've got another horizontal tangent line, another slope of 0. At x equals 3, we have a steep slope. This slope here is going to be positive. It's approximately positive 4. So what we can do is we can use those points to draw some points on the graph of the derivative. So when x is negative 4, the slope is 1/4. So the derivative is going to be 1/4. At x is negative 3, the slope is approximately 1. At x equals negative 1.5, the slope is down to 0. At x equals 0, the slope is down at negative 1. At x equals 1.5, the slope's at 0 again. And by the time we get to x equals 3, the slope's way up here at 4. So, the graph of the derivative is going to look something like this. Now we're moving on to question 8. Question 8 deals with the epsilon delta definition of limits and deals with this particular limit statement. The limit as x goes to 3 of x squared equals 9. Part A asks us if epsilon is 0.1, we want to find a delta such that if the absolute value of x minus 3 is between 0 and delta, then absolute value of x minus 9 is less than epsilon. Basically, this statement means that x is within delta of 3, and this statement means that f of x is with an epsilon of 9. So what we're going to do is we're going to try different values of delta until we get one that works. Let's say delta equals 0.1 as our first guess. Well, if we pick delta equals 0.1, if absolute value of x minus 3 is less than delta, that means x minus 3 is within delta of 0, so x is within delta of 3. So that means that x is between 3.1 and 2.9. So what we're going to do is we're going to figure out what is f of 3.1 and what is f of 2.9. And f of x is going to be sandwiched between these two guys. Well, f of 2.9 turns out to be 8.41, and f of 3.1 is 9.61. You notice these numbers are not within epsilon of 9. This statement is not true. And the reason is because the distance of these from 9 is about 0.6, but epsilon is 0.1. So we need these numbers to be closer to 9, which means we need a smaller value for delta. So let's try delta equals 0.01. In that case, x is going to be within 0.01 of 3. So x is going to be between 2.99 and 3.01, which means f of x is going to be between f of 3.01 and f of 2.99. f of 3.01 is 9.0601. f of 2.99 is 8.9401. If f of x is between these two numbers are between 9.1 and 8.9. So f of x is within epsilon equals 0.1 of 9. That means that delta equals 0.01 will work. This is a value of delta that is okay. In question 8b here, we're actually going to construct an epsilon delta proof. We're going to actually use the epsilon definition of a limit statement, to prove this limit here. The fact that the limit as x goes to 3 of x squared does in fact equal 9. So the first thing I want to mention is, what is the statement we're actually trying to prove? Well, we want to show that if epsilon is given, there is a delta such that if the distance between x and 3 is bigger than 0 and less than delta, then the distance between f of x and 9 is smaller than epsilon. So what we're going to do is we're going to expand this statement at the end here and see what it really says. Well, f of x is x squared, so really what we're trying to say is the distance between x squared and 9 is less than epsilon. X squared minus 9 factors as x minus 3 times x plus 3. If we're taking the absolute value of a product, it says we're taking the absolute value of x minus 3 times the absolute value of x plus 3. Now, no matter what delta is, this thing, the absolute value of x minus 3, is going to be smaller than delta. Now, what do we know about absolute value of x plus 3? Well, we know that if delta is less than 1, x is certainly going to be less than 4, because x is going to be within delta of 3. And if delta is less than 1, x is going to be between 2 and 4. So x is going to be less than 4, which means x plus 3 is going to be less than 7, which means absolute value of x plus 3 is certainly going to be less than 7. Because x can't be a negative number, so it can't be like smaller than negative 10. Okay, so we know this thing is less than delta, and this thing is less than 7. So what we want, basically, is we want 7 delta to be less than or equal to epsilon. So we're going to pick delta to be less than or equal to epsilon over 7. So delta here is going to be whatever is smaller between 1 and epsilon over 7. Okay, it's not going to be 1, it's going to be here 0.9, so that it's actually smaller than 1. So if delta is this minimum, then delta is smaller than 1, so absolute value of x plus 3 is less than 7, and delta is smaller than epsilon over 7, less than or equal to epsilon over 7. So this statement here, absolute value of x minus 3 times absolute value of x plus 3, this statement here is going to be smaller than 7 delta, which is going to be less than or equal to epsilon. So therefore, this whole thing is less than or equal to epsilon. And this whole thing is just an expanded version of f of x minus 9. So this statement is true, so absolute value of f of x minus 9 is in fact smaller than epsilon.